Today in this video we are going to discuss about the concept of cyclotron. Cyclotron is a device which can be used to increase kinetic energy of ions. Ion may be positive or ion may be negative. Doesn't matter. Cyclotron can be used for both the charges, positive charge and negative charge. But cyclotron cannot be used for electron. Why? Because see, by using cyclotron we are going to increase the kinetic energy of ions. For example, hydrogen ion, helium ion, lithium ion. So like this, these are the positive ions. Even for negative ions also we can use. Ion means it contains nucleus. So it contains nucleons. Certain considerable mass will be there for ions. But whereas electron is a very tiny and its mass is very less. Mass of proton, one proton is 1836 times the mass of the electron. 1836 electrons mass equal to mass of one proton. So ion have nucleus, it has considerable mass. So for both positive ions as well as negative ions, we will use this cyclotron, not for electron. See, what is the purpose of increasing kinetic energy of the charged particle, positive ion or negative ion? See, whenever that ion have high energy, if that high energy ion can be used for bombarding some material, see, for it to take place of nuclear reactions, usually we will bombard with alpha particles. Okay, so alpha particle is a positive ion. When alpha particle is going to bombard the nucleus of radioactive element, then it kickstarts the radioactive reactions, radioactive decay. And these high energy ions even can be used in medical purposes in treatment of cancer to kill the cancer cells. We may use these high energy ions are going to collide with the cancer cells and it can kill the cancer cells without affecting much on the neighboring wood tissues. And also these high energy ions can be used to study nuclear structures. So these are the main advantages of cyclotron. These high energy ions can be used to kickstart nuclear reactions. It can be used to treat cancer cells in hospitals. Okay, and it can be used to study nuclear structures. How we are going to get these high energy ions? See, if we apply electric field, uniform electric field, if a positively charged ion is placed in the uniform electric field, it experiences electric force in the direction of electric field. So it will have acceleration. Acceleration is QE by m. When there is an acceleration, speed of this ion goes on, increases. So kinetic energy increases, half m v square. After traveling large distances, usually its kinetic energy increases a lot. Required kinetic energy can be achieved by moving this ion for large distances. See, when you want more kinetic energy, then the distance traveled by this ion is large, then the entire experimental setup occupies huge space. See, you all know the value of the space, value of the land we know. In metropolitan cities it will be very costly. See, even you can set up this equipment in Thar radar, where Thar desert, there land is cheap, but how can you transfer that high kinetic energy ion to required place? Impossible. So that's why we need to arrange the setup in a small region. So that can be possible with the cyclotron. Even by applying only electric field, we can increase the kinetic energy of the ions, but we require large space. In cyclotron, we are going to apply electric field and magnetic field simultaneously, and we are going to apply mutually perpendicular. Magnetic field and electric fields are perpendicular. That means this ion is going to move in a crossed field. Electric field increases the speed of the charged particle. Magnetic field rotates that charged particle in a small region. Okay, this is the basic concept of applying electric field and magnetic field simultaneously. Only electric field, charged particle will go in a straight line. We need large distance. When you apply simultaneously magnetic field, electric field takes the particle in this direction. Magnetic field rotates the charged particle in this direction. So the charged particle will be rotated in a small region. This kind of concept we have seen in current electricity. Whenever the length of the resistor wire is 1 meter, in meter bridge, we have used 1 meter as a straight wire. But whereas in potentiometer, length of the wire is 5 meters, 10 meters. So having 10 meters length of a wooden plank is difficult. So that's why in potentiometer, what we have done, this is 1 meter wooden plate over which a wire is bent like this. We have a 10 folds, then we will have 10 meters wire is arranged in a small region. So this kind of technique only we are going to use to arrange that long distance in a small region. For example, usually tailors uses thread. That thread will be a very long 1 kilometer or 2 kilometer long thread, but it can be arranged very small region over a one finger. If you can wound it, that entire 2 kilometers length of the wire can be wound and you will have this much size. That's it. The entire length of the thread is arranged in a small region. In that way, here also that long distance is confined in a small region in a cyclotron. If you want to confine it in a small region, that charged particle should rotate in a small region. That rotation responsibility is taken by magnetic force. So here electric field's force is alone increasing the kinetic energy of the charged particle, but magnetic field is going to help in revolving the charged particle in a small region so that that long distance can be achieved in a small region. This we will explain the entire concept in a simple way here. Just see. In cyclotron, we are going to use two halo discs. Discs should be identical in shape and size. So that's why whenever you have one halo circular box, this halo circular box is divided into two equal parts. Then you will get two identical Ds. Okay, the D inside is halo. That diagram we are going to represent here. See, this is one of the D. This is a D, halo D. Outside anyway one metal sheet is there of letter D. Inside also we have one more letter D. These Ds are surrounded by this curved path. Okay, this is one D. This is another D. You imagine here if Ds are not identical, then you imagine they are identical. Okay, these are the Ds, two Ds, identical Ds we have placed here with very small separation. Okay, Ds are halo, Ds are evacuated. Any air is there, we will suck it out. The air trapped is completely evacuated. Okay, we are going to apply magnetic field here by using strong horseshoe magnet or electromagnet. Here we are going to place a strong north pole of the electromagnet, and inside we will place a strong south pole. So whenever a north pole of the magnet and south pole of the magnet are placed like this, the magnetic field lines from north to south outside the magnet, south to north inside the magnet, between the poles magnetic field is uniform. Uniform magnetic field will develop. If north pole is located here, south pole located inside, it means magnetic field lines are going into the board. So the magnetic field developed here is into the plane of the board. But see here, magnetic field lies everywhere in this region, inside the disk, between the disk, even outside the disk we have. Magnetic field exists everywhere. Okay, now magnetic field is along the z-axis, negative z-axis. So we have to apply simultaneously electric field. To apply electric field, we may give positive polarity to this D and negative polarity to this D by connecting a battery, ordinary cell. If we do like that, the direction of flow of current is same. DC source cannot alter the polarity of the disk. So that's why here we are not going to use direct source, that is cell. Here we are going to use alternating source, that is AC source. AC source we are going to use here. This AC source is going to alter the polarity of the disk. For first half cycle, usually AC current will be like this. In the first half of the cycle, current will be in one direction. During the second half cycle, current will be in opposite direction. That means during the first half cycle, polarity of the D1 is positive, polarity of D2 is negative. D2 is negative. Okay, during the second half cycle, polarity of the first D reverses, polarity of the second D also reverses. So in this way, this oscillator is going to alter the polarity of the disk with a certain frequency. That frequency is frequency of cyclotron, frequency of AC source, frequency of source. It may alter polarities 100 times in a second, or maybe 1,000 times in a second, or 10 times in a second. We are going to adjust this AC frequency with the required frequency. See here, when we connect an oscillator here, for example, initially polarity of D is positive, polarity of D2 is negative, then electric field will be from D1 to D2. See here, it is very important. Magnetic field lies everywhere, but electric field lies only between the Ds, because these Ds, halo Ds, are metals. Metal is electrostatic shielding. So inside D, electric field is not there. Only magnetic field is there. Magnetic field is not equal to 0. Between the Ds, electric field is not equal to 0. Magnetic field also not equal to 0. But inside D again electric field is 0. Magnetic field is not equal to 0. Remember this is important. Okay. At the center of the disk, if we can place a source of ion, positive ion maybe or negative ion. If you place a positive ion here, positive ion at rest produces only electric field. There is no magnetic field. So initially there is no magnetic force on this. Only electric force will act. Electric force will act in the direction of electric field. So this charged particle starts moving in this direction. So when it is moving, magnetic field will be generated. That magnetic field, applied magnetic field, will interact. Now the charged particle is going to experience both electric force as well as magnetic force. Electric force in the direction of electric field. Magnetic force, see here, positive charge is moving in this direction, current will move in this direction. We know that we will come to know the direction of magnetic force by using Fleming's left hand rule. Here field is into the board, charged particle is going in this direction, so current will be in this direction. Magnetic force will act upward. Magnetic force acts upward. Magnetic force is a centripetal force. Okay, when a charged particle is thrown into a uniform magnetic field perpendicularly, then the charged particle traces a circular path. So radius of the circular path r is equal to mv by qb. See, in this case, mass of the charged particle is remains the same. Charge of the charged particle is remains the same. Applied magnetic field is remains the same. If velocity is also same, then radius will be constant. But here the electric force produces acceleration. Electric acceleration is QE by m. This acceleration is going to increase the speed of the charged particle. If the speed of the charged particle increases, obviously radius of the charged particle also increases. But when magnetic force is acting, magnetic acceleration also will act. This magnetic acceleration and magnetic force are towards the center of the circular path. They are centripetal. These two will change the direction of the charged particle, but they never increase the speed of the charged particle. So here the charged particle, when it comes to motion, it experiences both electric and magnetic forces. Electric force increases the speed, magnetic force changes the direction. So even though the charged particle between the D's experiences both electric and magnetic fields, but the velocity or speed increases due to electric, magnetic is going to change the direction. So here it increases the speed, obviously radius of the circular path increases. So now here field is inside, current is this side, so force acts upward, so this charged particle will turn like this. But while it is turning, usually the radius of the path goes on increases. So radius increases up to here. When it completes half of the revolution, it takes time t by 2. Time period is t by 2. By this time, this oscillator changes the polarity of the D's. Then the frequency of the charged particle, see, time period, frequency, both are independent of radius and velocity, we know already. Here radius is continuously increasing, speed or velocity is continuously increasing, even though the time period and frequencies are remains the same. So only our duty is that the frequency of this charged particle must be equal to frequency of the oscillator. So we are going to adjust this frequency, which is going to be equal to frequency of the charged particle. Then when it completes half of the oscillation, half of the revolution, when charged particle completes half of the revolution, by that time here polarity of the D's reverses. That means it completes half of the cycle. It completes half cycle, it completes half revolution. It completes full revolution, it completes full oscillation. That means frequency of source is equal to frequency of the charged particle. If it is so, then frequency of the charged particle is equal to frequency of AC source. This even can be called as oscillator. This frequency can be adjustable. If these two are equal, then we will say cyclotron is said to be in resonance. So whenever it completes half of the revolution, polarity changes. What is the advantage with the reverse polarity? See here. When charged particle is moving in this direction, electric field is in this direction, it increases the speed. When it reaches here, electric field is in this direction, force will act in this direction. During the next half of the revolution, this electric field is not reversed, it decelerates. So to avoid that, if the polarity of the D's reverses, then electric field will reverse. It will exert force in this direction, acceleration will be in this direction, the speed of the electron increases. Okay, as long as this ion lies between the D's, both electric force and magnetic force will act, both accelerations will be there. Electric acceleration increases speed. Once it goes inside the D, there is no electric force, only magnetic force. Magnetic force changes the direction, so radius of the circular path does not increases, radius remains the same. Once it enters into the between the D's, again radius increases. Here both forces, here single force. So the charged particle will move like this. It will move here. Once it is going to reach the radius of the D, if you allow further, it is going to collide with the D. So here we have increased the energy of the ion, but it is going to be wasted if it is going to collide with the D. That's why now we would like to collect this I kinetic energy by having exit here. Exit slit will be there. To deflect the charged particle, we are going to place a deflector. This is called deflector. Deflector, it consists of opposite. If it is a positive ion, here negative charge will be there. This negative charge attracts this positive ion. So this changes its direction and it can be collected out. This negative plate is going to attract this positive ion. So it deviates from its path and it can be collected here. This positively charged ion is having high kinetic energy. This high kinetic energy ion can be used for our required purpose. I said already, this high kinetic energy ion can be used for to kickstart of the radioactivity, to cure cancer in medical purposes, and it can be used for nuclear reactions, and even it can be used for studying nuclear structures. Okay, this is how we are going to get high kinetic energy ions. This can be used for both positive and negative ions. If you take negative ion, you have to apply the concept and you will get it in which direction it revolves. See here, into the board field, the positively charged particle is moving in anti-clockwise direction. So we are going to have exit here. Sometimes you may have exit here, sometimes you may have exit here, sometimes you may have exit here. Finally, we need to collect high kinetic energy. But in this cyclotron, usually we are going to get some theory questions in competitive exams. Those we will discuss now in detail. See. Okay, first point. See here, magnetic field B exists everywhere. It lies everywhere. That means charged particle is always having magnetic acceleration. Where there is a magnetic field, there magnetic force acts. That magnetic force develops magnetic acceleration. But the magnetic force and magnetic accelerations are changing the direction of the charged particle. This magnetic force and magnetic accelerations are not going to increase the speed of the charged particle. That means these are not going to increase the kinetic energy. This is simple thing. Second one, electric field exists only between the D's. Inside the D's, electric field is zero because D's are made up of metal. Metal is electrostatic shielding, so there is no electric field. That means energy of the ion is not going to increase inside the D's. Energy increases only between the D's. Okay, that means between the D's, we have both magnetic acceleration and electric acceleration. Electric acceleration is going to increase the speed. Okay, that means the charged particle have always accelerated motion. This is very, very important. Always acceleration will be there. Between we have two acceleration, inside we have only one acceleration. This is very, very important. Okay, Magnetic force can be used to revolve the charged particle. Electric force can be used to increase the energy of the charged particle. This is the role of both electric field and magnetic fields. So, condition is we have to adjust the frequency of oscillator. Frequency of oscillator is equal to frequency of revolving ion or frequency of revolving charged particle. Then we will say cyclotron is in resonance. Okay. Now, with what energy it is coming out, that we should calculate. Kinetic energy of the ejected or kinetic energy of ion which is coming out of the cyclotron is half mv square. V is velocity of the ion. So velocity of the ion can be calculated from the formula R is equal to mv by qb. Why? Because radius of the circular path is equal to m into velocity divided by q into b. See here, velocity is increasing, radius is increasing, so it is moving in a spiral path and it comes out. Okay, by the time the radius of the revolving ion is almost equal to radius of the d, then we will exit the ion. So that's why this R is going to be radius of the d. Radius of the d, that is equal to mv by qb. And we need velocity of the ion just before exiting the cyclotron, that is qbr divided by m. Okay, so kinetic energy Ke is equal to half m v square, that is q square b square r square divided by m square. Mass cancel. So kinetic energy of the ejected ion is Ke is equal to q square b square r square whole divided by 2m. So with this energy, this is going to come out. Okay, if you like this concept, you please subscribe my channel Sharath NEET Academy, and also you share this information with your friends, and you please press the bell icon so that you will get the notifications very quickly. Whenever we upload a new video, you will come to know quickly. Thank you.